and we'll try to cover question answering with Hugging Face transformers and also time series forecasting for weather prediction. This is just one time step ahead weather prediction. And okay, so let us open the collab notebook here. Yeah. So this is the paper enhanced deep residual networks for single image super resolution. So let us just see this paper in brief. And this is enhanced deep residual networks for single image super resolution is like these are all extensions of this whole field of super resolution started from SRCNN, which is an algorithm from Dong et al. And this paper already has many citations. So the idea is that given a low resolution input image, can you generate a high resolution output? So if you just yeah, so if I give you this input, can you generate this ground truth? And as you can see from this like in a visual manner, it's very difficult to construct this kind of original images, even like even for a human to understand what who is this is very difficult, right? But uh, deep neural networks, convolutional deep neural networks, they are able to do this. And one such algorithm, which was the state of the art when it was published, so this is 2017, somewhere around that. It's called Enhanced Deep Residual Networks for Single Image Super Resolution. Now, why we call it as single image super resolution is because the idea is that we do not have a, a, a labeled data set here. What we typically do is we take the ground truth, we break it down into many sub images, and then what you would do is you would do a bicubic interpolation to take the ground truth to the low resolution, and then from that low resolution image which has been generated from the original high resolution image, you would typically build a model which would map from this low resolution to this high resolution. So you are basically having a single image, right? So that's why we call it as single image super resolution. So we'll let's give this a read. So recent research on super resolution has progressed with the development of deep convolutional neural networks, DCNN. In particular, residual learning techniques exhibit improved performance. In this paper, we develop an enhanced deep super resolution network with performance exceeding those of current state of the art super resolution methods. The significant performance improved of our model is due to optimization by removing unnecessary modules in the convolutional residual network. So what are the what is a residual network? A residual network is a network which has got a skip connection, right? So we also additionally, rather than just going in a forward manner, doing the convolutions in a forward manner, we also have this skip connection, and we can also call this entire block as a res block or residual block. So they say that they remove unnecessary modules in the conventional residual networks, And the performance is further improved by expanding the model size while while we stabilize the training procedure. And we also propose a new multi-scale deep super resolution system, which is they are calling it as MDSR, and a training method which can reconstruct high resolution images of different upscaling factors in a single model. And this is what is being very popularly used in downscaling the climate or weather predictions these days. And the proposed methods show superior performance over the state-of-the-art methods on benchmark datasets and prove its excellence by winning the NTR. This there was this super resolution challenge. So this model has actually won this super resolution challenge in 2017. So image super resolution problem, particularly single image super resolution, has gained increasing research attention for decades, and it aims to reconstruct a high resolution image, which is ISR, from a single low resolution image, ILR. So generally the relationship between ILR, which is the low resolution image, and the original high resolution image, IHR, can vary depending on the situation. And many studies assume that low resolution ILR, so image which is the low resolution, is a bicubic downsampled version of the high resolution image. But other degrading factors such as blur, decimation, or noise can also be considered for practical applications. And there are these studies which have shown significant improvement in the using for single image super resolution using deep neural networks. Now what you have to note uh, in this kind of problem is the metric that is used to assess the performance. So it is known as peak signal to noise ratio, or PSNR. So you can see that here this we have the PSNR, and there is another metric which is known as the structural similarity. So peak signal to noise, you would, if you are performing a downscaling task, or if you are doing a super resolution, developing a super resolution algorithm, you would be using this. At least you should use this peak signal to noise ratio as a maybe as a loss function, or even to, or maybe to track the accuracy of your model. And however, such networks exhibit limitations in terms of architecture optimality. And first, the reconstruction performance of the neural network models is sensitive to minor architectural changes. So you change the architecture, the performance changes. By changing the architecture, we mean by increasing the number of layers, decreasing the number of layers, adding skip connections, having dropout. Also, the same model achieves different level of performance by different initialization and training techniques. Thus, carefully designed model architecture and sophisticated optimization methods are essential in training the neural networks. The second most exciting super resolution algorithms treat super resolution of different scale factors as independent problems without considering and utilizing mutual relationships among different scales in SR. As such, those algorithms require many scale specific networks that need to be trained independently to deal with various scales. And exceptionally VDSR. So VDSR is a very deep super resolution, can handle super resolution of several scales jointly in a single network. So by scale, we mean that if you are trying to go from a resolution of, let's say, 10 kilometers to 5 kilometers, that's a 2x improvement in the scale. But if you are going from 10 kilometers to 1 kilometer, that is like going 10x, right? So that is what they mean by handling several scales jointly in a single network. So using VDSR, you can actually scale up even higher. And like there are the different networks, they are scale specific. So you can only scale as much, right? And training the VDSR model with multiple scales boosts the performance substantially and outperforms scale specific training, implying the redundancy among scale specific models. Nonetheless, VDSR style architecture requires bicubic interpolated image as the input that lead to heavier computation time and memory compared to the architectures with scale specific upsampling method. Now there was another method which is called as SR ResNet, so super resolution ResNet or super resolution CNN, which is also a ResNet, which has residual blocks. Successfully solved those time and memory issue with good performance. It simply employs the ResNet architecture from He et al. So this He et al. Paper proposed the ResNet architecture, and they without much modification. However, original ResNet was proposed to solve high-level computer vision problems such as image classification and detection. Therefore, applying ResNet architecture directly to low-level vision problems like super resolution can be suboptimal. So this problem of image classification is just you have to classify that the image contains a cat, a dog, or different classes, or whether you have to detect. It's a quite high level problem, right? I mean, you are not going into the details, but image super resolution for image super resolution you need to improve the pixel level information in the input image, right? The coarse resolution image. Therefore, applying ResNet architecture directly to low level vision problems like super resolution can be suboptimal. Okay. And to solve these problems based on the SR ResNet architecture, we first optimize it by analyzing the and removing unnecessary modules to simplify the network architecture. And training a network becomes non-trivial when the model is complex. So it's you have a non-trivial training when you have sufficiently you increase the complex by increasing the complexity of the model. We basically mean that we would increase the size, or we would add things which are like the residual blocks or the dropout layer, or you have a complicated loss function, and thus we train the network with appropriate loss function and careful model modification upon training. So we experimentally show that the modified scheme produces better results. And second, we investigate the model training method that transfers knowledge from a model trained at other scales and to utilize. Okay, anyways, yeah, so there is this data set known as div 2k, so which is a benchmark for image super resolution algorithms. Anybody who has made a new image super resolution algorithm must test their performance on this div 2k dataset, and you should compute PSNR and structural similarity. Okay, so there are these other there are related works. So there is VDSR, and so here you can see they have mentioned about Dong et al. They who first proposed the deep learning based super resolution method. Various since then various CNN architectures have been studied for super resolution. And okay, so in their method they basically modify the ResNet architecture, and they also improve upon the SR ResNet. So this was the ResNet architecture wherein you have a low resolution image as an input, and it goes, so you perform convolution batch normalization, nonlinear activation using ReLU, and again convolution batch normalization, and then you have an output, and then you also directly have this skip connection, and that is the residual block that you're having, and then you add both of them and then pass it through ReLU. So this is from layer L to layer L plus 1, going like input, the initial input is a low resolution image, output will be high resolution image. Whereas in the SR ResNet, you can see that they don't have the ReLU, right? So in SR ResNet, they have removed ReLU, they have kept everything else as same. Whereas in the enhanced deep residual networks, EDSR, so they just have con, ReLU, and con, and so they don't have batch normalization here, and so they basically remove batch normalization, and that's improving the performance substantially. So this is the fundamental block of the EDSR network that they are having, and you can see that they are also proposing a multi-scale super resolution network. So in multi-scale super resolution network, you have convolution and you have these different rest blocks, and you have this 2x, 3x, and 4x. So you can see that, and after that, you are basically having a common rest block, and then it's going to another rest block and then convolution, and then they are getting summed. So then again you break this into 2x, 3x, 4x. So in a single framework, you can perform multi-scale super resolution. So they have shown the performance of even multi-scale model, and the evaluation on the div2k dataset. So let's say, okay, so this is the ground truth image, right? So they are zooming over this region. So the ground truth or the high resolution is this one, right? Now bicubic interpolation gives you, you just have a low resolution this high resolution image, take it to low resolution using bicubic, and bring it back to high resolution using bicubic. So you can see that with bicubic interpolation, you can see that although the size of the matrix that becomes equal to the original high resolution, but your pixel level information is lost, right? So you have got a blurred image, and this is similar to your if you are doing this kind of work on, if you have a precipitation or a temperature map, and then you can see that, okay, so this is an A plus algorithm, and then this is SRCNN. Okay, so SRCNN is better than bicubic. You can see the PSNR increase from 21.41 to 22.33, and structural similarity also increased from 0.48 to 0.54. This one looks near to this, but still is not very good. So then this is the VDSR. Okay, so VDSR performance is, so the PSNR is 22.62. Okay, so this is, you have to compare with this one, and this is for SR ResNet, which is showing 23.14, and here this is EDSR. Okay, so which is, they're calling it as EDSR plus, so which is showing 23.48 decibels. This is actually visually also, this is looking most near to the ground truth, right? So if you see the finer details, if you see the finer details in the ground truth and in the high resolution image, this is looking most nearest. And similarly, if you see the from this second image, so if you zoom over this region, so this is the ground truth, and you can see that these are the detailed, uh, in the high resolution image, the detailed edges and the crisscross pattern. You are getting a very hazy pattern in bicubic, and in SRCNN is slightly improving, but now you see EDSR plus. Okay, and even SR ResNet is good, but EDSR plus is actually very good. Yeah. So then, yeah, even in this example, so then they show their performance in terms of this kind of a table and some benchmark results, conclusions. Okay, so this is the EDSR model, and the EDSR architecture they say is based on SRSNet, consists of multiple residual blocks. It uses constant scaling layers instead of batch normalization layers to produce consistent results. Instead of using L2 loss, the authors employ L1 loss, which performs better empirically. And our implementation only includes 16 residual blocks with 64 channels. Okay, and alternatively, as shown in the KRS example, image super resolution using efficient subpixel CNN. We have seen what is a subpixel CNN briefly in the theory. We will try to cover this subpixel CNN as well. So you can do super resolution using an ESPCN model, and according to the survey paper, EDSR EDSR is one of the top five. There is some kind of noise. Uh, can others also hear this noise? No.
No, sir.
Okay,
No,
fine.
sir.
Okay, that's okay. So you can do super resolution using ESPCN model, and according to this, okay, yeah. So, however, this has more parameter. It has more parameters and requires more computational power than other approaches. It has got a PSNR value of around 34 decibels, slightly higher than the ESPCN, which has got around 32. Okay, so as a survey paper, as far as EDSR performed better than ESPCN. So this is a survey paper on comprehensive review of deep learning based single image super resolution. So you can see that you have the PSNR here, ESPCN, SRSNet, and these are the number of parameters here in EDSR model. So its performance is actually like amongst the top five that they are saying. Okay, so let us import these libraries, and let us select a GPU for training the model. Okay, so yeah, so we use div2k dataset, a prominent single image super resolution dataset with 1,000 images of scenes with various sorts of degradations divided into 800 images for training, 100 images for validation, and 100 images for testing. We use 4x bicubic downsampled images as low quality reference. So this is the div2k dataset that we can download using div2k data.download and prepare. So this is an object of this class that we are creating. So this will give us a dataset with 4x scale. Let us download this dataset. Okay, once you do that, what we will do is we will do some pre-processing. So the first is flip images to the left and right, and this outputs random values from. So you would basically uh, do a flipping from left to right, and uh, images to left and right. Okay, and then you would also you can rotate images by, for example, in this case they are doing with rotating by 90 degrees, and then you will do random cropping. Okay, so the low resolution images of size 24 cross 24, and you are choosing this high resolution images as 96 cross 96. So the low resolution crop size is high resolution crop size divided by scale. So you use this double of this the operator, so that if you get a decimal number, that will discard the decimal part. So we will just, because the size cannot be in decimals, right? So this function will basically crop the images. Okay, and then we create a tf.data dataset object. So we augment the training data with random horizontal flips and 90 rotations. Okay, so yeah, which gives us train ds and val ds. So this is similar to what we have seen in the previous classes also. So you just map, you perform the different pre-processing operations, rotate, flip, left, right, and you do a prefetch. So which one is running right now? Okay. Okay, we'll just very quickly say this. Okay, and then you can visualize the samples. You can visualize the high resolution, low resolution images, and we define the PSNR loss function. So which is from the tf dot image. Uh, so inside TensorFlow there is a image class, and which has got the PSNR function defined. So you just pass a high resolution, low resolution, and these are image datasets. So the image datasets have values from 0 to 255. So the max val is 255, and then we will build the model. So we have seen that this is the basic building block of an EDSR model. So this is our EDSR model. So we inherit this EDSR model class from TensorFlow.keras.model class, and so you create two functions here. One is train step, and another is predict step. Okay, so train step will perform the training, and so first what we will do is we'll get our x and y. We will get our x and y from the data, and we'll say with tf dot gradient tape as tape. So we have seen this tf dot gradient tape. If you remember, we have discussed the TensorFlow tutorials in detail. So you would say, okay, so y pred is equal to so self of x comma training equal to true. So you would perform a forward pass, and you will then compute. So you will compute a loss, the loss between y and y pred. So this self dot compiled loss, so this will be defined in tf.keras.model. So that is why we are able to directly use this. And so what are our trainable parameters or vars? So we have self dot trainable variables, and gradients equal to tape dot gradient. So you compute the gradients, the derivative terms, and then using this the optimizer. So which is okay. So you apply the gradients, which is you are performing the gradient descent, and then you update the metrics. So which will basically track the loss. And in the predict step, you will just what you will just is do is the the prediction. So first you will do a TF cast, TF dot expand dims axis equal to 0. So basically, if you will just do with x, so you need an additional dimension which corresponds to the number of samples. So that is why we are performing a TF cast and TF dot expand dims. So then you will just create this high resolution image and clip it from 0 to 255 and uh, do rounding to the nearest integer. And okay, so removes the dimension of size 1 from, okay, yeah. So this is what your EDSR model is doing. Now you have the different functions that you need, which are defined here. So first is rest block. So in the rest block, you have you have conf and add, and then we have this upsampling layer. So this is the upsampling block. Yeah, so this is the upsampling block. So you first perform a con 2D operation, and these are the number of filters that you have. This is the kernel size. So you say padding equal to same, and then oh man, so much. Yeah, so then you have tf dot nn depth to space. So let us see what this is. Tensor flow and then depth to space. Okay, so this function basically rearranges data from depth into blocks of spatial data, and this is the reverse transformation of space to depth. So more specifically, this operation outputs a copy of the input tensor where values from the depth dimension are moved in spatial blocks to the height and the width dimensions. So yeah, let us see if you have this as an example. X equal to you have a list of lists as 1 2 3 4, and so this operation will output a tensor of shape 1 2 2 1. So this the depth to space will give you 1 2 3 4, and so for an input tensor with large shape, so of here of shape 1 comma 1 comma 1 comma 12, this operation for block size of 2 will return the following tensor of shape. So this is 1 comma 2 comma 2 comma 3. Okay, so that inherently your total number of elements remains the same. So it's basically some kind of rearranging the data. So we will so this upsampling, in like generally you can understand it as basically increasing the size of the input. So you pass an input and it will upsample that input. So then we see that you have this function make model which will create the model. So we define an input layer. So input is equal to shape, so of shape none comma none comma 3, and so we first perform scaling pixel values. So you scale with 1 by 255. So just divide all of the data with 255 because 255 is the maximum number, and then you say this, okay, so x equal to x new, and which is equal to, so you perform the uh, layers dot, so you perform the con 2D on x and assign it to both x and x new, and now we have these 16 residual blocks. So this is the rest block that we have. So now we have the 16 residual blocks, and with these 16 residual blocks after that, so you apply on this x new, and so now the further our further you apply con 2D operation, and then add, so to add to this x, this X new. So this is the residual connection, right? And then we will perform the upsampling and another convolution, and you rescale the values back to 255. So you multiply all the values with 255, and you say, yeah, so and then we will return the model EDSR model, and the input layer as input. So this is the input and this is our output. So we can see that in this EDSR model we have already defined our self comma data. So we will open this data x comma y equal to, and so this will basically make model will basically create the model for you. And here you can see we choose the number of filters as 64, number of residual blocks as 16. So you can basically change the number of residual blocks. And then the optimizer that we use is the Adam optimizer, and so you perform a learning rate decay also. So as you increase the training, you basically decrease the learning rate by using some formula. And then compile the model. So we use the loss function as mean absolute error. However, the metric that we are using is peak signal to noise ratio. So this is just to track the accuracy of the model. And then we will say model dot fit train ds per 100 epochs, and steps per epoch is 200. So let us see how it performs. This will take time. Okay, so that was all about the EDSR model, or enhanced deep residual networks for single image super resolution. And you could improve the model accuracy by training the model for more epochs, as well as training the model with a wider variety of inputs and mixed downgrading factors, so as to be able to handle a greater range of real world images. Okay, so then the next thing that we should discuss today is, okay, I don't think what is the time. We have time for Hugging Face question answers. We will see time series forecasting for weather prediction. Okay, let us open this in Colab, and let us stop this because otherwise we can't use the GPUs. Okay, so we have terminated this session, and let us open this one. So we will change the run type to the GPU here. Yeah, so this notebook requires, okay, so let us import the libraries. So in this example, what they are doing is they are using climate data time series, which is from Max Planck Institute of for Biogeochemistry. So let us see this data. So this is the website for Max Planck Institute for Biogeochemistry, JENA, and This shows the for, I think, for different locations, this shows the air temperature, the relative humidity, air pressure, precipitation, and daily precipitation sum. Okay, so this is the wind direction, and this is the net radiation, carbon dioxide concentration, surface temperature, and this is the weather sensor, and this is the weather camera. Okay, so this is the data set, and so you can see that from the table, we have the name of the columns, or the variables which are available, which is pressure in millibars, temperature in degrees Celsius, potential temperature in Kelvin, dew point temperature in degrees Celsius, relative humidity in percentage, saturation vapor pressure is in millibars, and this vapor pressure is in millibars again, vapor pressure deficit, specific humidity, water vapor concentration, and this is the relative humidity, wind speed, maximum wind speed, and direction. So also it's good to see how they have constructed this in Markdown. So you should learn basics of Markdown also, and you can see they have created this nice table using this simple Markdown syntax. Okay, so we will first download the data, so which comes in uh, this Jena Climate 2009 to 16. So we will see what is there in the data. So let us see DF. Okay. So you can see that we have the time, the pressure, temperature, in degrees Celsius. We have all these variables, and here we have time, right? So 0 0. So at every 10 minutes. So at 0 0 10 0 0 20 30, and for from 1st of January 2009 until 1st of January 2017, at every 10 minutes you have this data, right? So raw data visualization. So to give us a sense of the data we are working with, each feature has been plotted below, and this shows the distinct pattern of each feature over time period from 2009 to 2016. It also shows where anomalies are present, which will be addressed during normalization. So these are the titles, these are the feature keys, or the name of the variables in the pandas data frame, the colors for different visualization. So we will just see the plot of these data sets. Okay, so you can see that we have the pressure, temperature, and all these. So it's a huge data set, right? So 10-minute data set for 2009 to 2016, and this is the temperature. You can see the distinct seasonal cycle here in the temperature plot, even in the dew point temperature, relative humidity, saturation vapor pressure. So seasonal cycle is visible in all these plots. We have wind direction. Wind keeps changing its direction, so we have it all over the place. And then we will plot the heat map for the correlation amongst different variables. So you can see that okay, so this dark blue color is -1 correlation, plus 1 is the positive correlation. So how different variables are linked to each other. So wind velocity, maximum wind velocity, and this one last one is wind direction. They are having very less correlation with the others, right? Except except wind, there is a good correlation or good relationship between the other variables. So here we are picking 300,000 data points for training. Observation is recorded every 10 minutes. That means 6 times per hour. And we will resample 1 point per hour. So since no drastic change is expected within 60 minutes. So we do this via the sampling rate argument. So time series data set from array utility, and we are tracking data from past 720 timestamps. So 720 by 6 is equal to 120 hours. And this data will be used to predict temperature after 72 timestamps, that is after 12 hours. And since this basically means that you take the input of 720 timestamps, right? And which basically means so you have the data for 120 hours as input, and you are telling what will happen after 12 hours, right? So since every feature has values with varying ranges, we do normalize to confine feature value to a range 0 to 1 before training the neural network. We do this by subtracting the mean and dividing by the standard deviation of each feature. And 71.5% of the data will be used for train the model. That is 300,693 rows. Split fraction can be changed to alter this percentage. The model is shown data for the first 5 days, that is 720 observations that are sampled every hour. The temperature after 72 observation will be used as label. So you can see that we are using a split fraction of 71.5, and this is the step. So it is 6. So we measure the variables 6 times per hour, and for the past 720 timestamps. So for a particular date timestamp, you have to take the past 720 timestamp as the input, and the future is after the 72th timestamp. And the learning rate that we'll use is 0.001, batch size of 256, epoch as 10. So we will compute the mean and the standard deviation. You normalize the data by mean and standard deviation, but only using the training data, right? So we can see from the correlation map few parameters like relative humidity, specific humidity are redundant, and hence we will be using uh, to select features and not all. So you can see that the specific humidity and relative humidity, for example, they are saying that, yeah, so they have got a very good correlation with each other. So you don't need to include both of them. So it's like just representing the same thing, and therefore they are using only some selected features. So we will run this. Name normalize is not defined. We did not run this. And so we can see that the selected parameters are pressure, temperature, saturation, vapor pressure deficit, specific humidity, airtight, and wind speed. Now coming to the training data set, the training data set label starts from 792 observation. So you start at past plus future. So what is past? Okay, so past is 720, future is 772. So start at past plus future and end at start plus train split. So where do you have your train split? So train split is we can print it here. So we can see that we have computed the train split. It is at 300693. So that is where we end the we end the training, and you can see that so x train is equal to train data. So for I in range 7 dot values, and so y train you select the features from so I log start to end, and so this is the so start basically means you start at 792th, and then you end at 792th plus, or you okay, so the start here is 720, right? Oh, what, that's the past. So start, okay, so past is 720 and future is 72, so start is 792, and so this will be start will be 792 and end will be 300693 plus 790 plus 792, and this is the sequence length that we will be using. So let us see what is the sequence length in integers. Okay, so the sequence length we can see is 120, and this is because we basically will merge all the data set within an hour. So we just are not concerned about sub hourly variability. And now this the time series dataset from array function takes in a sequence of data points gathered at equal intervals, along with time series parameters such as length of sequences or windows, spacing between two sequence windows, etc., to produce batches of sub time series inputs and targets sampled from the main time series. So you can see that this pre-processing time series dataset from array. So you just have to give it X train, Y train, and you have to give it the sequence length, sampling, and batch size, and it will do all those things for you. It will create the input and the target datasets. So we then create the validation data. So must not contain the last 792 rows, as we won't have the label for those records. So last 792 we just want to keep for the prediction. And then we have, so we take this we create this input layer, and we have the LSTM from keras.layers, and in the output we have layers.keras.dense, so which is having a single output. So you are just predicting one value after the 72th timestamp or after 12 hours. So you create the model, compile it, and let us see the model summary here. Okay, so this is the model summary. So the input has got the shapes. So inputs dot shape one, comma inputs dot shape two. So this is the number of timestamps that is going in the model 120, or this is the number of hours. So 120 hours is going, and these are the seven is the number of variables. And we will create some checkpoints like. We will save this model in this file model checkpoint.h5, and we also use early stopping. So early stopping is will track the or will monitor the validation loss and make sure that the training loss, so not the training loss, the validation loss doesn't start increasing or start becoming higher than the training loss, so just to prevent overfitting. And so this is the, okay, so this is what this will do is this will track the validation loss, and it'll save the model, save the best model only in this file. So once at every iteration, so whenever it will find the loss is minimum, uh, so validation loss it will track, and if it encounters an improvement, it will save the weights in the model checkpoint.h5. So then you can run model.fit. Okay, so this is running, and you can visualize the loss, the prediction. So this was about it, I think. Yeah. So you can run this at your end and see this in greater detail. So one really nice thing that I liked about this example was using the Keras function. So this function to create the data set, right? Otherwise, you can do this on your own. You can manually create your own function to do this, but this is a clean way of creating the input and the targets. Okay, so with that, we will end today's class. And if you have any questions,